Now, what is the application for simple harmonic motions or resonant and natural frequency in the real world? We have pendulums, resonant frequency. The pendulum swing back and forth at its resonant frequency. Since the acceleration of gravity does not change if we stay in the same place, the only factor that affects the resonant frequency is the pendulum's length. All pendulums of the same length oscillate with the same natural frequency. Now, there is something we need to define beside the natural frequency is the forced frequency. Now, how to define forced frequency? If you have a kid who's on a swing, you give him a little push, he'll start to swing back and forth in a certain natural frequency. Then you need to wait until the right moment when he's retracted all the way to the back and push him again. Then now the swing will go higher with the kid. Then you wait until the right moment before he decreases the speed. Then you push it stronger. Then this wing will go even at a higher, at a max height than the first height. In this case, we say that in physics, the amplitude is getting increased, and the force you applied at the right moment when the swing was going back to you is called a forced frequency. You're applying force so that you can increase the amplitude of the natural frequency of the system. The frequency is the same, but the amplitude, or how far the swing goes, or how high does the swing make the kid go above the ground, that's called forced frequency. Now, when your forced frequency that we explained matches the natural frequency of the system, then in this case, you are creating a mechanical resonance. So you can define mechanical resonance, the increase of the amplitude of oscillation of the system as a result of a periodic force whose frequency is equal or very close to the natural frequency of the system. You know that now we're having very high buildings, and they're challenging the engineering and physical concepts of this world. Those buildings, to be able to withstand the strong winds and earthquakes, they install dampers inside of them so that they can handle the wind. The wind is able to push the building. When the wind is very strong, then it can push the building with little force. But this repetitive little force can generate some oscillation, and it could let the building collapse or reduce the lifespan. That's why in bridges, in skyscrapers, in very high buildings, they design them in an aerodynamic way where it can handle the wind, same as what you do for cars, same as what you do for airplanes. It is important to keep in mind no sharp edges, everything is curvy so that the wind can go through that building without generating that much force that could collapse that building or reduce his lifespan. Another application for simple harmonic motion is the quartz clocks. So before we have pendulum clocks, those pendulum clocks are depending on the pendulum swings to be able to tell the time based on the cycle of the pendulum. And pendulums, they used to have different timings and they have delays. So they used to put a little mechanical device that can push the pendulum every while so that he can keep the same period and the same swinging speed, if you will, so that the time will always be accurate. These days we have quartz clock. The technology of clock design and manufacture different so much from the time where we have pendulum clocks. So the quartz clocks today are very accurate, and they are commercially feasible, and they are small in size as well. And they have a very high accuracy than the pendulum watch, where you have 1/2000 of a second a day of delay for those watches. So how does the quartz clock work? It works on the principle of resonance. Each quartz clock have inside a tiny little crystal of quartz, and the quartz is a mineral material that naturally forms into crystals. It has a unique property that it will bend when a voltage is applied to it. If a pulse of a voltage is applied to it, then the crystal will begin to vibrate at its resonant frequency. So once the quartz crystal is set vibrating, the circuitry of the clock times successive voltage pulses to synchronize with the frequency of the crystal. The synchronized voltage provides the forced frequency to keep the crystal oscillating, just as pendulum in the pendulum clocks back in time that need to be synchronized forced frequency to keep them from running down. So this is the watch, typical design for watches we see today. Those quartz watches having a quartz element. This is the quartz element, and inside this box you see the quartz crystal in a tuning fork style, and you see those are being connected to the circuit. You give it a positive and a negative, so it is given in many cases 1.5 volts. So when you give it a volt, it will start to vibrate as a tuning fork, and every single while you need to give it a volt again to continue vibrating at the same speed or at the same period. So that's how it works. Before, we have a pendulum swinging right and left. Before it starts to reduce his speed, you need to give him a mechanical push so he can continue swinging at a certain rhythm. Here we have the two plates here that are made out of quartz. If you apply a voltage to them, 1.5 volts in specific for watches, then it will start to vibrate relative to each other. Before it stops vibrating, you give it another pulse, and so on. And most watches oscillate these days at 32.768 kilohertz of frequency.